that's not right. Okay. Oh. All right, so let's get started. So first of all, I apologize. I have no idea what's going on with my laptop. I'm pretty sure this class is cursed at this point. So I taught summer all fine. I've been doing this thing all 3 years I've been doing here. And I showed up 30 minutes early to get everything prepped. So yeah, I don't know what we're going to do about that. But we're going to start and hand out a bunch of stuff. Oh, so my name is Marissa Shepard. I'll be taking care of you this quarter. So right now I'm handing out periodic tables, and so I printed them on special cardstock for y'all, so you should cherish them, and so you can write all your cheat sheet notes on them. And so I'm still debating whether to make your test open note or not. So at the very least, you would be allowed a cheat sheet such as this. In the past, I've been doing open note exams. This is kind of a larger class. But yeah, since this is a larger class, I may change the exam style up a little. We'll kind of go with that as the quarter progresses. Okay. All right, so also, this is a large class, so up at the front, I'll have all your assignments. Here we have your homework, so I can pass those out, and then also our lab. All right, so let's take attendance, I guess. I really hope this note loads, or else we're going to have a really awkward time. I don't want to lecture on the whiteboard, given that we only have one little whiteboard in here. And so I did take over this classroom since it was large enough to accommodate y'all, so I can't fit in 112 due to technical issues. So why I do this, by the way, is I live stream the lecture, so currently we're streaming live to YouTube. I will post the link later. I just didn't want to give that away and then have people not show up on the first day. So that's why I did that, but I'll post that later so that if you can't make it to class, you can join in on YouTube. and, say hi in the chat, so I have all that running. I'm pretty upset with OneNote right now, but that's another story. No, this is the old notes. Every other note will load except for your current class. It is upsetting me a lot. So you have to open it in the full desktop version. So I was going to go over that. So I do post my notes. And so let's take a look at the Blackboard shell and our syllabus. So syllabus is here. And so unfortunately for y'all, you will have to be in Blackboard a little bit. And so again, we'll go over the syllabus. So your grade is going to be based upon these things. And so the only thing that you need Blackboard for, so if you really, really hate Blackboard, we do have the reading questions in there. And so you don't want to forget about them. And so they're under each week folder. And so we have the Chapter 1 and Chapter 2 reading questions. So you notice, right, we're doing Chapters 1 and 2 this week. And so homework is there. So you can put turn in homework either in person or on Blackboard. Either one is fine. And then so we go back to the syllabus. So we have our reading questions. So those are on Blackboard. Homework. So I'll print out homeworks for y'all. You can pick them up. And then they're generally due by the next week. And then quizzes. So if you notice your schedule, right? So we have class on Tuesday, Thursday, and then we have this kind of block time. So we really have lecture right from 11 to 1 essentially. And then on Thursday, right, that last hour is technically recitation, but that's just time set aside for our quiz. So our weekly quizzes will happen. And so we will have a quiz this week, but it'll just be a welcome assignment. So like, why are you taking this class? What are your interests? So nothing to study or stress about this week. And then the subsequent weeks, we'll be having our quiz on the chapter we covered the first week. And so you can kind of see how we do it. So we do start lab this week as well. So we have the popcorn lab. And again, I have those printed out. And just for y'all, so I haven't been like checking pre-lab questions. You don't have to like stress about that or anything. So just, you get it, you do it, that sort of thing. And labs are generally due a week after you do them. So if you have, the Tuesday lab, it's due next Tuesday. Thursday lab due next Thursday. And so we follow that similar pattern. Again, very consistent. Quizzes every week. And then, of course, you can see when we have our exam. And then continuing forward, so it tells you what labs we're doing. And so do note week 9. So we will not have lab on Thanksgiving week. So, of course, we have a lab section on that Thursday. So that means we can't run the lab that week. And then we will do a lab final and checkout probably on week 10. We have that scheduled, so you can put that kind of on your radar. And then we'll also be doing a journal summary, so I'll have more details about this assignment, but basically we're going to work towards kind of doing a research project with maybe a culmination at the end of 3rd quarter. So hopefully you stick with me throughout the 200 series, and then we get to the last quarter, probably do like a poster research presentation. Yeah.
Was there a specific time limit on the reading questions on Blackboard?
I don't think I made them timed, so I put them untimed. So if you look, it is one attempt, so you can't just do it multiple times, but I believe I left them untimed so you can, look through the book, read it. Yeah, you should be able to save it, come back, exactly. So I didn't do like a force complete on those. And if I did or something, just let me know. But it's supposed to be unlimited time for the reading questions. And let's see. So I'm looking at my lab sections. Is everyone sign up for the class that needs to be in the class? Or are there people that like need to get off the wait list? Because I only have one person on my official wait list. My thought is to try to squeeze everybody in. So I'm only looking at the regular wait list right now, but then I could go through the labs. So I have, and I probably am going to butcher this name, Mesash? Meshach? Okay. So you are here, but then I have other people waitlisted for lab, which I shouldn't. Because I have. All right, what's your name? And then I'm trying to see if you're in this class. So you are. Interesting. Okay, we're probably going to have to do. Sorry, I'm trying to figure out what's going on. Because the math doesn't add up. I have 4 waitlisted for one class, for one lab, and I have an empty space in another, but I only have 1 wait list here. So somewhere something the math doesn't add up. Math is not cursed. I love math. Right now, just my computer seems to be cursed, which is it's kind of upsetting me, but that's okay. Oh my goodness. What happened? Sorry. I'm going to get this going again. Okay. We'll let that thing about its life. Oh, did it finally load? Okay, I think it finally loaded. I don't know why. All right, so we'll be able to do that. So is everyone enrolled in lab lecture recitation? And unless you're the one person who has talked to me about taking lab separately. All right, so make sure you're enrolled in all 3. And so I don't normally take attendance, but we will the first day. And so if I butcher your name, just let me know, or you go by something else. Now's the time. Gregory A. Thank you. Celia? What is it? Celia. Okay. Tyler. Bates. Joseph B. Joseph Baynard. Going once, going twice. Okay. Jen Sperry. Phoenix. Andrew B. Madeline. Rebecca. Luis with a C. Logan. There you are. Sabrina. Grace. Craig. Craig D. No Craig. Juliet. Crystal. Anthony. Cora. Joshua. Audrey. Peyton. Savannah. Alyssa. Riley. Jonathan. Eugene. Anne. Is that how you say it?
Is it A-N-H?
Yeah.
Yeah,
Anne? Or on? On. Okay. Kayla? Madden. Matthew K. Carmen. Breezia? Breezia with an L. Okay. No. Aliro? Aliyah? Or Aaliyah? Aaliyah, sorry. Alexa? Marlene, I think, was going to be absent. Is that correct? Salvador? Victoria R. Oh, Tori, I should have known. Angel, Hunter, Katie S. And one more page, Brandon S. Matthew Smith, Nicholas Snowden, Janet, Camilla, Camilla, okay. Gabriel, Gabe, Zitong, Christy, and I'm sorry, one more time that, yeah, Meshach, okay. I have to I gotta write that, phonetically. All right, excellent. So if you have lab today, show up to lab today, including if you're on the wait list. So I'm still trying to sort through what the heck is going on because my numbers do not match. But we will sort that out. We will find space for you. We will do that. All right, other things that I wanted to talk about. So I am also, as it stands, the Earth Club advisor. And so I highly encourage you to join Earth Club, but I wanted to plug a secret plug to you guys because, I feel like not enough people are interested in Earth Club. Like it has a bad, maybe, I don't know, perception. And so what I'm finding is more students really want like outreach, so they want to do like outreach activities, and so that's really what I'm passionate about. So I almost want to make it like a science club instead. That might be more popular. And so I have some things brewing in my behind the scenes of reaching out to like homeschool communities, and I would like to maybe host a science fair on campus. So I'm trying to see interested students, so this would be a great opportunity for y'all, kind of do some teaching, some leading of, whatever group. So this is still in the works, but yeah, we're talking about it. So I want to recruit people for Earth/Science Club. And I'm also, so this is more like a reasonable goal, I would say. And so with that, I can't spell. You're going to learn that I can't spell. So I can do math, but I can't spell worth anything. So feel free to correct me on my spelling. And so this seems reasonable. I would maybe like to write up a paper on this and get people involved. And then I have kind of this long shot goal. I don't know how feasible it is, but I have had students kind of be interested. So I have a large class. So I'm recruiting from y'all because y'all are the 200 people. And so I'd like to do some research, specifically looking into probably more like sustainable reactions. And that's kind of like the green chemistry area, maybe even running organic chemistry reactions in water, which, again, this seems long-shotty, but if we keep it green, maybe we can do some reactions. I've been in touch with SOU, and they would let us get our grubby hands on the NMR over there, and that's really what we need to kind of do research. So if this seems interesting to you, we can chat after class about either one of these. So again, this would be like kind of more reasonable, but if you really wanted to try to get into the weeds of research, we could come talk to me and kind of figure out what we can do. All right, anything else I want to say? Well, all right, so welcome to chemistry. And so, I already knew chemistry had a pretty bad reputation when I, wanted to be a chemistry instructor. But as I've continued teaching, I've learned that it really does have a really bad reputation, and that's because of the math, right? So first thing I'm going to say, right, is I want you to succeed. So remember that. So I'm here for you. And so most people, right, struggle with the math. So come get help with me. And so you'll find, too, so I'm pretty lenient with due dates and everything. I'm hoping that won't backfire on me this quarter because, like I said, this is the largest class I've taught here at RCC. But, I have an understanding, so, right, you're doing the labs, and then you get stuck on some math parts. So I don't want you to rush and turn in like a half-finished lab, right? I want you to come get help with me, come learn how to do it correctly, and then turn it in. But obviously, right, I can't have all 48 of you turning in on week 10, right, 10 labs. I just can't physically grade that much. So I am pretty lenient. I don't take off points for being late or anything, unless it becomes an issue in here. So just, try to be respectful, try to keep up with the class, but, get help. Again, I am here for you, I'm available. And so usually I have office hours just after class, out of convenience, because that's when y'all are on campus. But, I'm available, email me, we can meet, by Zoom, anywhere. We have to meet at a coffee shop, like whatever we have to do. Like, I want to help you, especially, get through the math. And the math shouldn't be too bad the first quarter, but it's kind of like the second quarter and third quarter, there's a little bit more like algebra and like solving quadratic equations that some people get a little nervous with, but you should be fine at the math level. But I don't want the math to scare anyone from chemistry, is what I'm saying. And I know chemistry's scary. She's a cruel mistress of a subject. Been teaching in a while. All right, and then my email's on the board, so that is the best way to communicate with me. So mshepard@roguecc.edu, and so that's Shepherd spelled like the sheep herder spelling. So I had changed my maiden name to Shepherd, thinking that Shepherd would be easier to spell, and I was completely wrong. So yeah, just make sure you spell it correctly. And if you sent me Blackboard messages, I apologize. I do not read those. They go into the ethers. So email is the best form. Question?
Can you show us how to open the OneNote document from Blackboard? I can sit with you later too.
Yeah, so basically you have to download the OneNote 2016 version. That's what I use on this computer. And like sometimes you have to hunt for it. So I'll put that. So OneNote 2016. So again, you need the full desktop version. Yeah, question?
I think they do get, I think the school does offer OneNote 365 and other stuff like that for free for the school.
Yeah, so exactly. So if you poke around in like your Microsoft 365, you should be able to download it. So it's different from like the OneNote app. The OneNote app won't open it, but it has to be the full OneNote. So that's why I say like sometimes if you search around for the OneNote 2016, then that's like the full program. But yeah, if you need individual help, like definitely ask me during lab too. That's a good time to kind of work through things. And I do also do the PDF. So I do blank PDF notes that I provide, and so that is on there. And then ideally on Thursday, I'll post the week's lecture, with all my scribbles on there, so you have that. And then if I don't post the notes on Thursday, feel free to yell at me. That's the one thing that I am admittedly bad about doing. So, if you send me that email, like nagging, that will light the fire under my butt. All right, so let's kind of survey the class. So kind of what is chemistry? Why are we taking this class? What are our interests? Let's hear some interests.
Oral health.
Oral health. So I'll put that under medicine. And so, right, we could totally go into fluoride and all that, or other alternatives, different toothpaste, and
Studying biology, ecology.
so biology, ecology. And so, of course, you can get into like laws with that. So this is also like super fascinating. So, right, it's great to understand the basic chemistry is what's going on. But then I always tell people, right, you want to get involved in your local issues, your local governments, like understand everything, understand the laws. And, it's really, you got to have an understanding and then try to figure out kind of, I guess, the compromise and all our crazy laws and regulations to function. What else we have?
Ecohydrology.
Ecohydrology, wow. So
Probably fall under the sciences, geology.
is that like energy too, or?
Not really. It's more so like the relationship between water and the ecology. So a lot of it would be, it might fall, at least my, I don't want to get too much into it, but, it might fall into the sciences.
I'll put, hey, I love water. Water is fascinating, especially once you start like studying it more, appreciating like the chemistry of water. Like it is a beautiful solvent, it is a pH 0, like, I mean 7. I don't know what I'm saying today. pH neutral. All right, what else do we have in here? Marine bio. Where can I put marine? So again, more water chemistry is pretty important. Are you going to take oceanography? Nice. I taught that over this summer. What else do we have? So vet, so a lot of medicine, right? And so with medicine too, we want to know our units so we can give people proper dosages. Are we in milliliters, milligrams? You know, there's all sorts of conversions. What do we need to do? So all that's really important. What else do we have?
I don't know if this would go under, but can't forensics be like chemistry and
Oh yeah, I think they're going to offer a forensics course at some point. I kind of put it under this like toxicology. That's a good way. Forensics. What's the best way to kill somebody without being detected?
Insulin?
Huh?
Insulin?
Insulin?
I thought that's what I've heard.
Oh, that's a good one. I have my own answer. I like other ways to kill somebody. Yeah, but then that would be detected with forensics. That's right what I was thinking. So deuterated water is the way to kill somebody. If you replace all their water with deuterated water, do you guys know what deuterium is? The heavy, yeah, it's like heavy hydrogen. So you have H2O, so that's regular water. And then D2O would be heavy water. And so why I brought that up with toxicology is it would be really difficult to detect D2O. You would have to take like a IR spectroscopy to see the difference in stretching. So that would probably not be a usual toxicology test. Anyways, any other thoughts in here, connections?
Like material science, like metallurgy,
Yeah.
metals react.
So metallurgy, and I'll put under there like alloys too, because that's really important. And there's people say like we've lost a lot of knowledge of alloys too, that like back, I guess probably when they were in the heydays of when they just started making swords and stuff, that they had better like formulas, I guess, for the alloys, and now we don't have those same ratios, so our alloys are potentially weaker. So yeah, good area of research, and of course learning like how to prevent metals from being like oxidized. And other thoughts in here? And so I'll also add some things. Of course, for chemistry, I always think of two big things. At least, you know, all my cohorts kind of went into two branches, and that's going to be medicine. So, of course, drug development. That's huge money. So I like to put a bunch of dollar signs there. And then the other one is going to be ag. So, right, a ton of it goes into agriculture, so there's a lot of money there. And you'll hear me talk about this a lot, the Haber-Bosch process. And obviously this is not balanced, but just this basic reaction of hydrogen plus nitrogen gives us ammonia. And so what is ammonia essential for? Fertilizer, exactly. So, right, a ton of energy goes into this Haber-Bosch process to make all that ammonia that, of course, we need to support our food production. And obviously, right, agriculture has been very successful in being able to feed our large population of the earth. And, you know, we can also add, like, pesticides to that, unfortunately. I don't like that, but, you know, that's what chemists do, unfortunately. You know, I'm not talking about the ethics of chemistry right now, but... Yeah, I agree. I mean, not to start like going down the rabbit hole, it's like plastics too. Like I think that's a big invention that chemists did that like maybe we shouldn't have invented plastic, because now what do we do with all those microplastics that are everywhere in the environment? Like how do we solve that? And yeah, pesticides, exactly, right? We make these horrible toxic substances and then they end out in the environment, then how long are they staying in the environment? So, yeah, chemists, you always got to think about the consequences, but unfortunately that doesn't really happen, so. And of course, right, I'm biased. I like chemistry, so of course I like this graph here that chemistry is the essential science here. And we didn't really relate it to nuclear chemistry, but this is, of course, a good area to hopefully go into. I know TerraPower up in Washington has been doing a lot of research on new nuclear technology. And then, of course, we have math and physics over here, our nice friends. We like them. All right. And so we'll basically be looking at chemistry. And so chemistry is just defined as the study of matter. And so, right, matter is just anything that has mass and takes up space, from this desk to, of course, the air. And so we look at both chemical changes and physical changes. And so, of course, a chemical change is where we have a rearrangement of atoms. And so, right, usually something is used up or consumed and then converted to a different form. Of course, right, conservation of mass, so nothing's lost, just rearranged. And so I'm sure you've seen combustion reactions before, anything from lighting a match or, right, you start your car, obviously you have to have that combustion. And of course, we'll also look at physical changes. And so physical changes, if you recall, matter does not lose its identity, so it just changes states. And we'll just be focusing, right, on the three main states, solid, liquid, gas. So just keep that basic. And obviously the example that probably everyone is familiar with is water. So of course everyone's seen water in all three phases. Your solid ice cube, your wonderful water that I'm sure many of you are drinking, and then heating it up for steam. All right, so now we start kind of with the scientific method. And so let's kind of look at this. So, right, we have, I call this like our oversimplified, rosy picture of science, right? And so you start off with some sort of observation or curiosity or some problem you want to accomplish or solve. So, right, you form your hypothesis or do your experiments and kind of keep repeating. And so either, right, you succeed in making what you want to make or prove what you want to prove, and then this should be consistent and contribute to the body of knowledge. And then, of course, right, you publish it, yay, everybody's happy. And so we'll look at the differences between a law and a theory. All right, so let's look at let's define some things. So what's qualitative data?
Observations on something that don't involve like counting it.
So observation, I'll put that doesn't include numbers. And so what are some examples of what qualitative data would be?
Color or smell.
So color, smell, put gas under there, or just general reactivity. What do you notice? Does it spark? Does it ignite, fume? And so then what is quantitative data? So the numbers. So yeah, either, right, mass, so we can get the mass of something, counting, so something that we can accurately measure. This could even be, right, concentration. This will be something that we'll look at. Of course, mass and length, all those would be quantitative data. Density is important a lot in chemistry. And so now let's go back to kind of the scientific method and how it works or doesn't work. So what's a hypothesis?
It's something that can be tested.
So we'll say a question that can be tested. And so, right, you do your experiment and then you confirm some things, but now, what's the difference between a theory and a law? It might be easier if you give examples.
A law, I think, is something that is observed, like, over, dozens of experiments, but you don't entirely know why it happens.
Exactly. And then can you give an example? Or someone else can also tag in, not to put all the pressure on.
I'll let someone else tell you.
Law typically refers to something that occurs with most, if not all, experiments.
It should be all experiments, but then what would be a good, so what's a good example then of a law? Yeah. So gravity, right? So what's the equation for gravity? Object note down.
9.8 meters per second squared.
You guys are killing me. Okay, now you're making me look up the formula because I don't remember it.
There's like a 9.8 somewhere in there. I feel it.
No, the gravitational constant of the Earth is 9.8 meters per second squared. That's the constant of acceleration.
I was trying to find a nice formula. So, right, we have G equals GM over R squared. We'll just put something simpler. F equals MA, right? Everybody knows that one. So any formula, right? So now we're going to see it's basically, just like she said, any observed relationship, right? So it's going to be any formula, then essentially we can plug in. So all the gravitational formulas, right? Kinetic energy is 1/2 mv squared, that'd be 1. Right, E equals mc squared. So you could go on and on, right, writing a bunch of formulas, but that's what a law is, right? So it's just a formula, it's just a relationship. And so, right, if we were dropping our pen, and if I had my formula ready, we would be able to figure out, right, our terminal velocity based off of the acceleration due to gravity. And then, right, we would do that over and over and over again. It would be consistent. But then, like we mentioned with the law, it does not provide any sort of explanation, right? We don't know why this is happening. We don't know why E equals mc squared. That's just the relationship. And so how does a theory then, what does it attempt to do then?
It has to offer explanations to those laws.
And so we'll say attempts to offer explanation for an observed phenomenon. And again, this might be easier to think of some examples. So what would be a theory? Yeah, Big Bang, so that's a good one.
Einstein's theory of general and special relativity.
So general. Other examples?
Theory of evolution.
Evolution. I want to say string theory has been disproven. Well, talking to physicists, the word on the street is that string theory can't ever be proven, and it was a cute thing, but they're going to move on quietly. I mean, plenty of people made their career off of string theory, but like I said, I don't think it can be proven, so it was fun, but yeah. Any other theories? So I think black holes, that would be more, because that's more observed, but then there would probably have to be like some sort of explanation as to why they formed. But I don't know that there's like a well-established theory on black holes. But the only other one I was thinking of was germ theory. And so, right, for all of these, and so it kind of depends. So I'll pick on germ theory because I feel like this one is pretty well established, right? So we feel like we've identified some viruses and bacteria, and they infect us and make us sick, and you know we have a lot of evidence for that. That seems really solid, but again, it's just a theory. So if there was new evidence, right, we would have to totally rethink germ theory. And so same thing. So I won't get into all these because of course these are fuzzier, but you know, again, Big Bang, there's a lot of evidence that we have an expanding universe, but of course, right, we don't know, are we forever expanding? Is there going to be some point where we, you know, reach our maximum and begin contracting? So there's a lot of theories with that, and obviously no one was around during the Big Bang to directly observe it and tell us, yes, this is exactly what happened. So, questions on these definitions? And so, of course, I want to talk about some bad science because, you know, your textbook always makes everything sound so good. And, you know, it's always like, oh, yeah, a scientist, right? Trust the scientist, all this stuff. But, you know, when you really get into it, you really have to, right, ask questions and be aware. And so, hang on, this link didn't work. But I will find another reference. And so kind of my warning is, right, so scientists are fallible just like everybody else, right? They're human beings. And so you have to think about what scientists kind of want too, right? So scientists are always competing for funding. And, you know, if you were to talk to any research scientists, that's always what they're going to be stressed about. And of course, you have to have data to back up, right, your funding. So what happens, you know, if you're not getting the data you need? And so that's kind of what I see with this thing. And again, I'm not trying to like completely destroy your faith in science, but you have to be able to ask questions. You have to look at the data. You have to, you know, be able to, you know, repeat it to really anything. And so not to get into too much into the weeds either of like chemistry and how it works. So when you publish something, right, like people just take your data at kind of face value. No one checks it, right? So there are reviewers, but all they do is they just read through your papers. And so there's actually one journal that does check the prep, so that would be Organic Synthesis, and that's like primo journal. So those things are tested, but that normally doesn't happen. And so this is a good example of a very egregious. And so you can see it's been retracted now, but it was published, so it did make it out. So now, will they not let us see it? So, oh, come on, I want us to see this. Let me see. It's kind of an older article, so I guess it kind of was hidden. And so this is a picture that was from their paper. And so, right, if you kind of look, and you guys are pretty smart, you know how to use computers, so that is clearly Photoshop, right? You can see that doesn't match the background. But this was in their paper. So there are 3 reviewers for every paper. That's pretty standard. So 3 people looked at it. Nobody caught that looks obviously Photoshopped. And so it was published. And then eventually, you know, people started looking at it and, you know, saw these little pictures. And unfortunately, since it's been retracted, we can't look at all the pictures anymore. I'm trying to see if I can find. So yeah, here are just some more examples from that paper. So this one's like super egregious, right? But again, that passed review. So that's always the issue. And so, right, science is supposed to be self-correcting, but you know that the time that it takes to self-correct is kind of unknown. So for example, there was something that came out in the computational chemistry world a couple of years ago, that whatever code they had written, because of the differences in operating systems, so like Linux versus Windows, they were actually spitting out different answers, but no one caught that for like 30 years. So, you know, again, science is self-correcting, but, you know, eventually. So, you know, we don't know the time frame, so that's why I always say, you know, you got to be critical, you got to ask questions, you got to see the data, you know, all those things. So always ask questions. And if the science cannot stand up to the questioning, then, you know, I would question the science, obviously. So that is the number one thing about science, right? Science is meant to be questioned. Like, I do not like, not to get political, but right, they always say, like, you know, trust the scientists. No, no. Question science. You must ask questions. That's, if you were to continue your chemistry journey and, you know, or whatever you want to do, if you want to go to grad school, right, you are going to be questioned. You're going to present your research and people are going to attack you. That's science. That's how it works. That's how you grow. That's how you learn things. All right, so that's research. And so now let's start with, well, how do we start doing chemistry and dealing with data? And so unfortunately, we have to start kind of boring. So we have to start with the metric system. Well, let's kind of orient ourselves. Like, what scale do scientists look at? So does anybody know? So what scale is a human hair on? You can just give me like millimeters, micrometers, nanometers. Yeah, micro. And so that's, right, a little micro. So that's a mu symbol. So 1 times 10 to the negative 6 meters, about the scale. So what about an atom, like a sodium atom? What scale are we looking at? Yeah, so that would be either nanometers scale, so 1 times 10 to the negative 9 meters. And then chemists also use their own special unit. Does anybody know what that one's called?
That's the one I remember.
What energy one?
I'm talking about attajoules.
Oh, attajoules, yeah. Attajoules is a special one, so that's 1 times 10 to the negative 18. You don't normally see attajoules. But what about for size? Anybody know? So moles is a good guess, so that's more with like quantity though, of like, you know, bigger reaction size. But what about an individual atom? Chemists have a special unit.
One atom.
So it's called an angstrom, and it's abbreviated like this. And so that's 1 times 10 to the negative 10 meters is what that means. And so you often see either angstroms or, again, the nanometers for that atom scale. So what about an elephant? How much does it weigh? How big is it? What scale are we talking? So either measuring in height in meters. What about its mass? How big? What'd you say? Yeah, so you're like kilograms, you mean? So like either kilograms. How many kilograms do you think an elephant weighs?
I don't know how to do tons to kilograms.
So how many tons does it weigh, you think?
Anywhere between 2 to 10 tons, depending on the species.
So 2 to 10 tons, you know, your elephants. So I think that's somewhere like 5,000 all the way to like maybe 15,000 pounds or something crazy. Or 5,000 kilograms, sorry. And then I'm not sure what the upper limit is, but. And so what about the distance to the nearest stars? So not the sun, but Alpha Centauri. Does anybody know that in light years by any chance? Not quite that many light years.
16.
I thought it was 4.35, but 2.4.
Says Google.
Oh, I'll take the. So light years. And so what is that in kilometers? Or roughly at least?
At least a billion.
So I've had it at like 4.3 light years, which translated to this number.
4.15 times 10 to the 14.
So you said 4.15 times 10 to the 14?
Yep.
Yeah, that's much easier than trying to count. I can't count. So yeah, extremely large there. And so, right, we're already seeing, so scientists look at a wide range of data, right? So either we're looking at stuff really, really tiny, or we're looking at stuff really, really large, so depending on your specialty. And so, of course, we have, first of all, our scientific notation. So are people familiar with this? I'm kind of assuming y'all are, but I don't want to rush. And so we're comfortable, right? So we know that this means a little negative exponent, while this is written as a positive. Does anybody need me to go slower on this? Otherwise, I'll move on. And so don't be shy to ask questions. And if you are shy and like have no idea what's going on, just talk to me after class if you don't want to speak in front of the class. But I guarantee you, if you don't know, somebody else doesn't know. And so then, if we're comfortable with our scientific notation, then we'll move on to kind of metric units. And so we'll start off with, so each type of measurement has a base unit. And so somebody mentioned moles earlier, so of course we have moles. And then we have meters for length. Grams is our base unit for mass, and then liters for volume. And then temperature, they have here Celsius, but we don't usually do like metric prefixes to Celsius. And then I'm going to really put under here Kelvin, because really we want to be in Kelvin, especially as we go down the line and do more thermodynamically relevant calculations, you would need to be in Kelvin. And of course we have seconds and bytes, but again, we don't generally do those in chemistry. And so I'm sure many of you are familiar with the metric system. And so we know, right, it's based off of multiples of 10 based upon adding your appropriate prefix. And so then we have this chart, and so notice, right, this is the multiple, or the multiplier, so this is, right, by the base unit. So this is saying, right, if it's 10 to the 9th, then we can write out what I would call our conversion factors. So for giga, right, 1 times 10 to the 9th meters is equal to 1 gigameter. This would be our conversion factor. And so we could do the same, right? So now let's look at atto, because someone mentioned it. And so like we said, that was 10 to the negative 18. This is, again, by your base unit. So let's just say, so 1 times 10 to the negative 18 meters then is equal to 1, right, attometer. And so the other thing is, so if you're comfortable writing like this, so when people start setting up their conversion factors, I usually encourage them to do positive exponents. Again, it doesn't particularly matter, but we notice, right, we can do a little trick. So multiply everything by 1, right? And so now that gives us 1 meter is equal to 1 times 10 to the 18th attometers. So this gives us our conversion factor in positive exponents. Everybody still with me? Again, I'm trying to figure out what level of math people are at too, so again, if I need to speed up or slow down, just let me know. If you guys are all bored out of your minds, we'll keep just speeding along. And so again, I'm not sure where our math skills are or what we've done before in other chemistry classes, but I would highly encourage you to kind of do the dimensional analysis method, where you kind of unit cancel. And so I will say, personally, I was totally against dimensional analysis when I was first learning chemistry, but it's really helpful. So I'll tell you, I made it through physics, right, through dimensional analysis and unit canceling. So super useful. So I highly encourage you to kind of set it up in this way. And so again, right, our conversion factors are just fractions that show a relationship, right? So this is just showing our relationship, just to be clear. And I'll again use one that we probably are familiar with. So we know 12 inches is 1 foot. And again, we can just write that relationship either way. And so this will be useful, right, depending on what converting we go to. So for example, if we have, right, this one, feet is on top, inches is on bottom. So that means I'm probably going to want to go from inches to feet then, right, using this conversion factor. So just as an example, if you want to go 50 inches to feet, then we want to be able to set up our conversion factors. So start with what you know. And then I say, right, conversion factor. Then you pick your appropriate conversion factor, right, with the unit that you want on top. So we're going to feet, so I would pick this one. So 1 foot, 12 inches. And so, right, I encourage you to set it up this way, and I think they call it the railroad track method. But now we can see, okay, my inches cancels. And so 50 divided by 12, let's just get a number real quick. Right, so 4.167 feet there. All right, let's do practice. See if we can do our converting. So convert 5.17 times 10 to the -5th kilograms to micrograms. So take a few minutes to kind of set this up, and then we'll go over it together and kind of see where everybody's at with this. How are we doing? Do we have answers? Does any brave soul want to put it on the board over there? Anybody feeling? Brave, you can also turn this around so you're not sure. Is this flip? No, this is not a cool flippy board. Flip it manually. Anybody want to come up and show us what they did? You don't have to be right either. Brave souls. Anybody want to go for it? There's no pressure. Huh? Everyone, see, everybody always doesn't like math. All right, you're Christy, right?
Yes.
Yeah, our first victim.
So I did it not like converting. I just like I thought about how many kilograms is in a milligram, and I got it was I counted 6 zeros, so I don't know how much is that.
Let's see. I'm not sure.
So that's a million. So in my opinion, 1 kilogram is equal to 1 milligram. So adding that is equal to 1 times 10 to the 6. And converting kilogram to milligram, so I did 6 plus 10, 6 plus 5, because it's 2 negative 5. So
I think you're kind of there, but you're a little off in the relationship. Yeah.
Is it kilogram to milligram?
Oh, microgram. So this is micro. So yeah, you would be correct if you were thinking milli. So can you do it for micro?
Micro? Is it, I need some help.
Oh, 10 to the negative 6. I wrote it.
6 zeros in front of the 1. 6 zeros in front of the 1 to the left.
6 zeros in front of 1. Oh, so it's like
Yeah.
the opposite.
Negative 6.
Negative 6. So, well, my answer was 5, 17 times 10 to the negative 11. That was my answer. Anyone else want to?
So let's stick with what you were trying to do, but then let's write out the proper conversion factor, right? So you had kind of this idea going, and so this is tricky to do, right? So I think this is kind of the harder method, is where you try to figure out, well, what's the relationship between those two? And so looking at those, right, you could tell that there's a 10 to the 9th difference. And so it should be, right, 1 kilogram is equal to 1 times 10 to the 9th micrograms. And so if you did that, you could determine an answer.
So for my method, it's to the negative 5, and we're converting it to something that has into the negative 6. So I just moved the decimal place one place. So I got
Ooh.
1.6.
Boom. Well, we got to think about what the kilograms mean. So that's what's killing everybody.
So yeah, we just convert it that. Someone else want to go?
So someone want to try? So I have at least one conversion factor, but there might be an easier way to do it. So some of you are like, you got this great idea that you're trying to figure out the relationship between these two, but you might be making your lives harder if you're not ready for it. Carmen, you want to go?
I just wrote out like what we initially had. I put 1.7, and then I did it like the railroad track method or whatever.
Yeah, so then put your kilograms.
Kilograms over 1, and then I want to get rid of the kilograms, so I put like 1 kilogram on the bottom, 10 to the 3rd, right? Grams on top.
So you're going from kilograms to grams then?
Yeah.
Yeah.
Okay, like, I don't know if this is wrong.
No, so I was gonna say, so that sounds like we're doing a two-step conversion, which I would encourage, which is good. It's not a bad thing. So we're going kilograms to grams to micrograms with Carmen's method. So let's see, and this looks good here.
And then I didn't know how to like combine these correctly, but I just put it like this times
Yep,
10 to the 9.
exactly.
I think the exponents, if you're multiplying them, they actually like are added together. So then the exponent would be 10 to the 4.
Exactly. Yep, for your final answer.
Do I have to like distribute the, like I could just put it right into this?
Yeah,
No,
because
yeah,
it's-
you
it's
just
the
can
same
add
thing.
them, yeah,
Yeah.
yeah. So then you can write, yep. So excellent mental math practice. So that's really important to do, is do your mental math. Because what I often find, and you know, I do have my calculator here. I will show you how to properly enter things. And so we'll go through this. So this is correct. But it's always good to give yourself a mental math sanity check. So what I find is somehow, some way, right, something gets entered wrong into the calculator. And so usually when you don't use the little e. So does everybody know? So let's say we want to write 5.17 times 10 to the negative fifth in this kind of calculator. We have to write 5.17, and then notice this little EE, so second E. So that means times 10. And then, right, then you put your exponent to the negative fifth. And so if you don't do it like this and you like type out times 10, it will screw everything up. You would have to write parentheses very carefully. But I find that's where the math errors occur with students, is they did not put this in properly in some sort of operation, and then they get spit out a completely wrong answer though. And that's why it's always good to do that mental math sanity check. Am I somewhere in the right order of magnitude of where I expect to be? And so if you kind of do that sanity check, then you can of course double check your calculator. Yeah.
Is that negative 5 an exponent, or is that just like
Yeah,
in the
so
regular spot, like where you put it in?
yeah, it's so right, that means that's the same thing as this, right?
Mm-hmm.
It's just the calculator, the E means the times 10 to the power of negative
Okay.
fifth.
So
Yeah.
you don't have to manually
Yeah, and
make
you
it
would
an exponent?
yeah,
have
and
to
you
go
would
in?
not want to do that, or else that's where the calculator gives you order of operation errors.
Gotcha. Okay.
Yeah. And so we'll do it this method. And so again, this was good, doing the step by step. And so right, if you're not seeing this, and you know, no fault in this, no shame, this is, I think, difficult for students to do, especially initially, right, when you're trying to learn this. So trying to see that this factor of 1 times 10 to the 9 difference between them, this is difficult. So just walk yourself, right, step by step. So do what I call, right, this two-step conversion. And then I always say, right, your kind of base unit is your safe space, right? So go from your 1 unit to your base unit, and then your base unit to the other unit, just like was shown there. So I'll just rewrite that. So again, we went kilograms to grams first, so we needed the grams on top, kilograms on bottom, then of course just writing the relationship, so that's what was done there. And then again, grams to micrograms, so grams goes on bottom, micrograms on top, and to give us our answer. And of course, again, if you had seen that relationship directly, so I wrote out our other conversion factor, where 1 kilogram is equal to 1 times 10 to the 9th micrograms. And so, of course, that would give you the same answer. I'll just write it out, so both answers are there. Let's do another practice on that one. Unit converting always gets people. Let's do another one. So let's try 600 milligrams to kilograms. Do we have answers? Do we need more time? Do you want to put it on the board for us?
Yeah, sure.
Markers over there.
So first, I looked at distance of micrograms and kilograms. Is it micrograms?
Milligrams.
Milligrams from just your base, the grams. So I found that they both went, they're both in quantities of 1,000. So one's negative 10. What's the notation again?
Yeah,
One's
10 to the
3,
negative.
one's 10 to the 3. And so I just wrote out 600 milligrams. One is 1,000. Wait, no. Milligrams, 1 gram. There we go. And then the milligrams cancel out. And you get 600 milligrams over 1,000. And then that I just turned to 0.6 over 1 gram. And then we did the same thing, but with kilograms instead. I think it's 1,000 grams equals 1 kilogram. No, just plus grams. Grams cancel out. You get your 0.6 over 1,000, and that just simplifies into 6 times 10 to negative.
Yep.
Sorry, my handwriting's really, really bad.
And so I just kind of wrote out his same steps just a little more succinctly, so I didn't bother calculating the intermediate, so just kind of putting it in one big thing. Did you have a question?
Oh, I was just gonna say that, the way I did it, I just kinda did it a different method, where I just looked at the decimal places and just moved it, like 6 over. Like I took the 600 milligrams and moved the decimal point 6 places to the left, because I know there's 6 spaces between that.
Yeah.
That'd be a good method as well, too.
Yeah, I think that's perfectly fine. And so I think it goes back to, can you see the factor between them? So if you notice, right, because all you're saying is there's a 1 times 10 to the 6 difference between them. And so I just like the math. Honestly, the zeros make me a little squirrely. But I can, write the conversion factor. So again, if you see it, go for it. If not, do the two-step. So then we say, right, 1 kilogram is equal to 1 times 10 to the 6 milligrams. And then, you can be fancy. So we have 6 times 10 to the second milligrams. So doing some mental math. So that cancels. So 2 minus 6 gives us that answer there for our mental math. Questions on this? Are we feeling okay? Not okay? Do we need more practice? I see. Okay, let's do some more practice. I see a lot of mixed faces. So let's convert 5.55 times 10 to the negative 7th, and let's go megameters to centimeters. See how that goes. And so definitely bring a calculator to class, especially bring whatever calculator you plan to use on your exam to class so you can practice and make sure you can punch everything in appropriately and know your calculator. Although we might get really good with the mental math of these metric conversions. Does any brave soul want to put it on the board for us? All right. So you're doing a two-step conversion? Perfect. I think that'll be, yeah, I think that's easier for everyone to follow. Not that you can't be ambitious, but
And then I converted meters to centimeters.
So excellent. So megameters on bottom, and so that was 1 times 10 to the 6 for the factor.
It was to the fifth, so I got that wrong.
Oh.
It's an easy fix.
And then centimeters, so centimeters on top, 100 centimeters, 1 meter. So what's our final answer?
Somehow I got 155 centimeters when I used the 5, 10 to the 5, converting to 21 meters, and meters, I got confusing myself with that. It seems like it should be 55,
Yep,
25 centimeters.
yep. I plugged it in, so I put it into our calculator, but of course we could do our mental math. So we have 5.5 times 10 to the negative 7, then times, so right, that's basically plus 8 from here. So negative 7 plus 8 is times 10 to the 1, so yeah, that gives us 55.5, but of course, feel free to use a calculator. Again, mental math is good, but good to do both. Excellent. Are we feeling better about conversions, maybe? So I think we'll move on for now, but we can always, again, revisit them. You can always ask me for help. That's what I'm here for. And so the next thing that we need to talk about as we're gathering data, and this will be really relevant in labs, so once you actually get in there and start doing stuff, well, we have to figure out, basically, with our calculations, right, how precise is our glassware? And so this is where the sig figs comes into. And again, you'll play with this in lab. So, right, our rulers can only measure so accurately, so like measuring by hand. And so just to get a little bit of the real world. Sorry, I can't draw either. But let's say we're trying to measure this notebook card. And I have my ruler next to it. And so, right, usually if we're using a metric ruler, it has hash marks every 10th place. So something like that. 1, 2, 3. And so that would be 6 there. And so, right, when you go to measure this, so of course you can kind of guesstimate. And so I see it right before that 2. And then you always want to report to 1 extra than what your glassware is showing, right? So you can kind of guesstimate that last digit, and that's as accurate as you can read it. So in this case, it'd be 5.1, and then that last digit, right, is uncertain. And so, I'm going to put it at 9. You could have picked 5.18, whatever. But this is, right, this is, again, our physical limitation of how accurately can we measure this. And of course, like, let's say you're using like electronic calipers, right? Those probably have much more precision, so maybe they go out to the hundreds or thousandths. So that if you were using, again, an electronic one, then you would record, right, every digit that your caliper gives you. So different levels of precision. And so you'll see that too with the glassware. And so, for example, right, we usually use what's called a graduated cylinder to measure liquids, and then later you'll also kind of at least touch upon the existence of these volumetric flasks, and those are like made to only measure one type of volume. So for example, like a 1 liter volumetric only measures 1 liter, and it does so very precisely. And then the glassware itself tells you the tolerance, and it tells you the inaccuracy. So all that relates to sig figs. And so let's kind of get into what are sig figs, what does this mean? And again, it'll become clearer as we do stuff. And so let's start with our conversion factors. And so, right, we do a lot of converting, but conversion factors are treated as exact values. So all this means is that we're not going to look at the conversion factors when trying to determine our sig fig. And so again, this is just infinite sig figs, so all of these, right, relationships. So don't worry about a sig figs there. So let's look at kind of these rules. And again, these rules make more sense as we do it in practice. And so we start with the first rule. And so all non-zero values are significant. So that's pretty straightforward. So in this number, we have 536. There's 3 digits. So that's called 3 sig figs here. Then our next rule is zeros between non-zero digits are significant. And again, that's pretty self-explanatory. I call this the captive zero rule. So, right, it's between 2 numbers that are significant. So therefore, that 0 must be significant. So this example, 6,703, right, that's a captive 0. So that is significant. So all 4 digits. And so now we have these next 2 rules. And so one is called the leading 0 rule. So it says placeholder zeros to the left of a non-digit 0 are not significant. And so what I say is this is showing, right, how small. And then if we look at this one, well, trailing zeros, so it says zeros to the right after a non-zero digit are not significant. So these are not significant, but this is just showing how big. And so I usually just summarize this rule for ease, because I want to just say if it's showing magnitude, right, it's not significant. And so the other way to think about that is, can you rewrite it in scientific notation and get rid of those zeros, essentially, and have them be meaningless? So write this one, so 1, 2, 3, so we could write 4.3 times 10 to the negative third. And so now this clearly shows that it only has 2 sig figs, so those zeros, again, they were not significant. They're just showing how small. So same thing with this 7,000. So we could write it, right, 7 times 10 to the third. So now we're clearly showing it only has 1 sig fig. And then, of course, this example, so we have, right, our captive 0, but then this last 0, right, is just showing how big, so that is not significant. And then, so our last rule is zeros to the right after a decimal point are significant. And so this, right, is showing how precise. So that is different. And so example, right, if you bother to add that extra 0 here, so 50.0, that means, yes, we know that precisely out to the 10th place that it is this value. And so that makes, right, the other 0 significant as well. So we have 1, 2, 3 sig figs for this one. And so this other example, 0.0600. So again, that would be 3 sig figs. So the first 0, that's just showing how small, so that's not significant. But then these ones at the end, that's telling you, yes, we measured that precisely, and so you need to write that. And so just keep that in mind for a lab. Like if you measure something and you think it's exactly 6 centimeters, you need to write 6.00 centimeters, showing that your ruler is accurate. Question?
I had this problem come up for me the other day where, like, I needed to have 3 significant figures in my answer, but my answer it ended on a 0, so it was like 110.1. And if I were to include the 0.1, then obviously it's 4 sig figs, but if I don't include the 0.1, then it's 2, so I didn't know what to do there.
This is, yeah, that's what so that's how you solve that, is with the scientific notation. So you're right, and you will probably encounter this at some point in your life. So just to recap, so you were saying, right, you got this answer, 110.1. Well, let's say it's 4 sig figs, and we really need it to round to 3. And we'll get to why we round and how we round in a second. So we're getting there. So just hang with me. But like she was saying, so let's say we wanted 3 sig figs for our answer. How do we show that, right? Because now if we write 110, well, oops, now that's only showing 2 sig figs, right? And so the trick is sometimes you may need to rewrite it in scientific notation so you can show, oh, that's a 0 after the decimal point. That is significant. So then when you rewrite it as a 110, you know, okay, all 3 of those digits are significant. So yeah, that's the way to get around that. And the other thing that you might see, and it's a question here, but the other way to get around that is to write it like this. So yeah, 110 with a dot after, except some people get confused by this, and you know, if it's like at the end of the sentence, that might look weird. And so it's a little ambiguous. That being said, you might see it, but that's what this also means, so 3 sig figs. But the rewriting it in scientific notation, this is the better, clearer way to indicate that yes, we have 3 sig figs. All right, so let's try the practice. So take a few minutes and figure out how many sig figs, and you can, of course, consult your neighbor. And so I encourage you, you know, make friends in here, make study groups, exchange numbers. And of course, you can do that in lab as well, but definitely make sure you exchange information so you can be friends later. At least chemistry friends. See, do we have answers? All right, let's go through them. So you all can just show me fingers. So for number 1, how many sig figs? Excellent. I see everybody holding 2. Very good. What about number 2? How many fingers? I see a bunch of 3s. Excellent, excellent. What about this one? 3 as well. Good. Didn't let all those zeros trick you. Number 4. See a 2. And then this last one. And so this was the tricky one, but looks like most of you didn't fall for it. And so yes, that was 2 as well with that weird period. And so like we mentioned, right, this might be a clearer way to write it out so we know what they're trying to say. All right, so now let's look at our temperature scales and how they compare. And so I assume people are pretty comfortable with the Fahrenheit scale. And so we know that. And so of course, right, water freezes at 32, water boils at 212. and there's 180 between it, so it's fairly awkward. And so Celsius and Kelvin, they're much nicer since they scale the same amount. So notice, right, there's 100 degrees difference between the freezing and boiling point in Kelvin and Celsius. And so they were made that way. And so what is Kelvin based off of? Yeah.
I don't know if you know, but like the heat engine, yeah? Okay, never mind. But like when air stops moving.
Oh, you're talking about like absolute zero and stuff, right? Or, yeah. So what's absolute zero then?
Like when air would like atoms would stop moving.
Yeah. So complete, I call it complete absence of motion. And I can't spell. But like you were mentioning, so it would be like molecular motion. So we haven't gotten there, but you probably know that electrons are always running around our atom. And so absolute zero would be complete absence of that motion. And so this is a theoretical point. I think they've gotten down to as far as like 0.4 Kelvin. I would have to look at the research. They're doing research, I think, at MIT, trying to get as close as they can to that. And obviously that's very difficult to do. It requires a lot of thermal isolation. And not sure what other tricks they do to get down there, but yes, exactly. So it's based upon that complete absence of motion. And so this is where I always, again, bring up that thermodynamic relevance. And so that's why when we, again, get there and do these calculations with the volume and pressure and kinetics, right, all of that depends on the Kelvin, since it's based upon absolute zero, so that corresponds to, again, the absence of motion. And so we can convert between them. So temperature Kelvin then is just equal to your temperature in Celsius plus 273. And I think your homework technically it says 273.15. But honestly, I never use the 0.15 because we don't have that level of precision in our Celsius temperatures. I usually ignore it. But I think the only place it becomes somewhat relevant is you have like a homework question that says like convert from exactly 1 degree or 0 degrees Celsius to Kelvin, and so there's where the answer is like 273.15. So that's all it's getting at with that question is the level of precision. But again, in the lab when you're measuring the temperature, it's not very precise, so you'll just get a whole number of like 20 or 23, and then you can add that 273 to that. And so, of course, the difference between Fahrenheit and Celsius is a little more awkward. And so I would not expect you to memorize this formula. So on an exam, if I wanted you to do the temperature conversion, I would provide it there. And so you can obviously see how to plug it in. So if you're going from Celsius to Fahrenheit, right, you plug in your Celsius temperature here, so times 9/5 plus 32. And so what's 9/5 equal to? So 1.8, so you might see the formula also written as 1.8, right? So don't let that confuse you or anything. So same thing. And so again, if you were going from Fahrenheit to Celsius, just watch the order of operations. So notice you have to do the subtraction first and then the multiplication. And so another very important property is density. So of course you can kind of figure out the identity of metals through this, and it would also be relevant for calculating different amounts. So you want to know like the density of whatever substance, so your solvents, hexane, or any other organic, or whatever you're working with. And so density is just defined as a ratio of mass to volume. So it's literally just this formula, right? Density equals mass over volume. And so it can be in a variety of different units, so just kind of depending on what you're given. So generally, it's in grams per milliliter, but you could see, right, grams per centimeter cubed, and so 1 centimeter cubed is equal to 1 milliliter, so this might be relevant. Sometimes you could also see something weird like, kilograms per meter cube or something strange. So just be aware, right? Other units exist. You can use your dimensional analysis to convert around. So just be cognizant. Yeah.
Can you talk a little bit about the difference between mass and weight?
So mass would be, right, like you kind of have a standard of comparison to, versus weight is going to be how much the gravitational force is exerting on you, right? So that's why they always say, like, you would weigh less on the moon, right, because it's less gravitational force, but you have the same mass on the moon. So you would have to compare it to, so, right, if you're on the moon, you'd be more like comparing, the scales of justice type of thing. So it's like 500 grams to 500 grams. So that's still the same mass, right? The mass hasn't changed, but the weight, again, is that force of acceleration and the pushing down. Does that clarify?
Sort of.
Yeah, so again, weight is just based upon the gravitational acceleration more. So yeah.
What gets me is that we use grams to measure mass, but then we can also use it to measure the weight of something.
Yeah. So it's just, I mean, that's right, our conversion on Earth, though. So then that's why, that's the difference. So if you apply it to the moon, right? But yeah, it's still the same equivalent mass, but it's just like for determining the mass, like there's actually an international standard of what a kilogram is, and it like exists in a little bubble, and like this is defined as a kilogram of mass type of thing. So that's kind of the difference. But you can obviously, right, convert between them, but yeah, it's just more semantics as well. All right, before we dive straight into this, is everyone familiar with the triangle trick? Anybody seen this?
Oh, I have seen that.
So I like the triangle trick. So you can rewrite this like the triangle trick. And then, so the trick is whatever you're solving for, you cover up, and then that gives you the formula. So let's say you want to find mass. So if you cover up mass, then it ends up being density times your volume. And so that's one way to do it. But you can, of course, right, also look at your units. So density, okay, if it's in grams per milliliter, times my volume, milliliter, yes, that gives me grams. So yes, that makes sense. So you can use both your dimensional analysis and unit canceling, or just the triangle trick. Oops. So again, let's say we're solving for volume then. So if we want volume, then that would just be mass divided by density. But again, we can see that. So if we have grams divided by density, so density is grams over milliliters, so the milliliter, if you're dividing, right, flip them, and so that gives you back out volume. So you can use triangle trick if you need it, but again, all dimensional analysis. All right, so let's try this problem. So if we have 73.2 milliliters of a liquid and it has a mass of 61.5 grams, what is the density? So let's start with that one. And then we'll do our multiple choice one. All right, does someone have an answer for this one? So density equals mass over volume. So you could either depend on your units, yeah.
I got 0.84 grams per milliliter.
and so grams per milliliter. And so we haven't covered this yet, but we're going to get there. So I'll say it. So eventually we're going to learn how to do the math with our sig figs. But we have 3 sig figs here, 3 sig figs there. And so our answer has to have 3 sig figs. So I'm going to tack a 0 on. But yeah, like I said, we haven't gotten there, so don't feel bad for not doing that. But yes, did we all get this answer? Yeah.
So when we're using sig figs and we're like cutting off some of the numbers that the calculator's spitting out, should we like write the equal sign normal, or should we do like this really like about equals?
I think it's fine to just do equals because, yeah, it's usually implied with these calculations that there's going to be some rounding because we do have, again, those physical limitations. But we will cover more rules tomorrow on how to do the addition, subtraction. So if you're lost, we will get there, / we'll talk about it in lab too. All right, let's try another example. I'm trying to finish up chapter 1, kind of running towards the bell at this point. So now, what is the volume of an object that has a mass of 455.6 grams and a density of 19.3? Huh? So you might want to double check that. Let's give everyone a minute or two. So use your triangle trick, use your dimensional analysis. All right, we're trying to get to volume, so centimeters cubed, which is the same thing as milliliters. All right, do we have answers? So let's vote. Who thinks A? Who thinks B? C? D? Yeah, and E. So it should have been D. So we have, for these, I like to look at our triangle trick. So we want volume, so it's mass divided by density. Or again, our dimensional analysis, so grams, then divided by density, so grams goes on bottom, centimeters cubed on top. And so the units work out to give you your units of volume. And so that was D. All right, last 2 minutes here. Let's just define intensive and extensive properties. So what is an intensive property?
Something like mass, like it's inherent to the thing that you're measuring.
So you're correct about it being inherent to the substance, but it's not mass, though. And so extensive depends on the amount. So that's the difference. So I'm going to put mass there. But what would be an intensive property? So what's an inherent property? Just covered it, too. What did you say? So volume would be extensive, right? So how much you have depends on the mass. So volume we'll put under extensive. Density. So yes, density is the one I was looking for just because we just talked about it. But what else could we have? What else is an intensive property? Any ideas? Charge would probably be a good one. Yeah, because that's based upon the atom. It doesn't matter on the amount. What else? How else can we characterize substances? What else do they have? So pH of a substance, how acidic, how basic. I'll add in there like acidity. So some of this goes into like organic chemistry too, and like how strong of an acid things are. What else do we have? I think simply too. it's not like, I guess we could put it like reactivity. Let's do reactivity at least, but what else do we have? Yeah, so color, and so we're running out of time, so I'll just add like melting point. So those are good ways to characterize how pure your substance is. Boiling point. You could also do the state of matter. So solid, liquid, gas. And then of course extensive, so we covered mass, volume. I'll just add length on there. But again, so this would depends on your substance amount. So that would change versus again your intensive properties. So it doesn't matter how big of a pile of caffeine you have, that will always have a consistent melting point, boiling point, etc. All right, we are out and over time. So we have a 30-minute break, and then I will see half of y'all in lab upstairs on the 3rd floor. If you are on the wait list, please come and we will figure out a place for you.